Okay. Next is 21 through 24. Find dy dx by implicit differentiation. Sure. Okay, so let's zoom in here. And so what we're looking at is e to the x. Good morning. Plus e to the y plus, equals, sorry, e to the x plus y. And they want us to find dy dx. Okay, so what's going to happen here is when we differentiate, the e to the x's, since we're differentiating with respect to x, are just going to become e to the x. However, when we differentiate anything with e to the y, we're going to get e to the y times the derivative of d to the y dx. Okay, because the chain rule is going to say, oh, y is a function of x, and so we need to differentiate that. There might be some funkiness that we have to deal with on the right side, maybe turning that into a product, but I'm going to forge straight through and just see if it works doing it without that. Okay, so in other words, we're going to take our verb dx and differentiate everything with respect to x. Understanding that y itself is a function of x. And so that's where our dy dx are going to come from. So just going left to right, the derivative of the natural exponential function is itself. It's kind of bizarre. E to the x. Technically, yes, we differentiate the x here, but it's just one. So this is e to the x. For e to the y, we're going to get e to the y. But then remembering that the derivative of e to the u is e to the u times dx of whatever that u is. Here our u is y. And again, it is some function of x. And so we need to add this chain rule part. So this is where we get our first instance of dy dx. And if you remember with implicit differentiation, this sort of becomes like a variable where we can solve for dy dx at the end of the problem. On the right side, let's think about what happens. We're going to get e to the x plus y, and then we need to differentiate this guy, which is going to turn into 1 plus dy dx. How do I get 1 plus dy dx? The derivative of x is 1. The derivative of y is dy dx. And now we have to sort of finagle this situation so we can get dy dx all by itself. So let's distribute and see what happens. E to the x plus e to the y times dy dx is equal to e to the x plus y plus e to the x plus y dy dx, where here I'm just distributing the e to the x plus y. We should probably put the things that involve dy dx on the same side and put everything else on a different side. So I'm going to accomplish that by subtracting this guy and this guy. And so we'll get e to the y dy dx minus e to the x plus y dy dx is equal to e to the x plus y minus e to the x. Now factoring out the derivative, we get dy dx times e to the y minus e to the x plus y. Oh, this is going to be fun. Is equal to e to the x plus y minus e to the x. And then dividing both sides by e to the y minus e to the x plus y. We get dy dx is equal to e to the x plus y minus e to the x divided by e to the y minus e to the x plus y. We're kind of like, oh, that sort of like looks the same, but it's not. This is a y, this is an x. Really nothing we can do there. So yeah, implicit differentiation. Understanding that when we're differentiating with respect to one variable, when we see a second variable, we have to assume that it represents a function of that first variable. Mario, let me take a quick look at 47. It looks like something we can accomplish in less than 5 minutes. We will. So for 47, they give you the velocity and they want the distance, bless you. And so you would just be taking the integral there. If we have time at the end, we can come back to that. But that's this understanding that the velocity is equal to the derivative of the position with respect to time. And so if they give you the velocity and it's invariably something that includes the natural exponential function, s is our position. And so in order to get s, we need to integrate on both sides. And so the position will be given by this integral. And so then we'll return to that if we have time. Okay, but we do need to keep on keeping on. So yeah, 5.5. I'm going to kind of give you a greatest hits on 5.5, stuff I think you need to know. And I'll do this. These are my notes. That's the place to do it. So 5.5 is called other exponential and logarithmic functions. Other, it's a loaded word. What you mean, other? Did I hear a squeak of a question? No? Okay. False alarm. Or is it not false? Is somebody asking a question? I don't know. What's happening? Okay. Let's see. Present this today. I think we're going to start by kind of reminding us where we've been. Okay, so other, what the heck does other mean? Well, something that is not something else. Other. Recall. Because stuff does tend to get, not confusing, but there's a lot of new rules and formulas that we've been throwing at you for the past week. But where we've been so far is that with the natural log, we convinced ourselves that the derivative of the natural log of some u is equal to 1 over u times the derivative of u. And going in the opposite direction, that means that the integral of some 1 over u du is going to give us back the natural log. Or again, we're sort of thinking of the derivative and the integral as opposite directions on the same street. They are inverse operations. And then from the natural log, we looked at the natural exponential. And said that its derivative, where it is e to the u, remarkably, is just e to the u, with some correction in case u itself is a function. Well, chain rule action. And so then the other way down the street tells us that if we're integrating the natural exponential function, we get back the natural exponential function. And these are nice and pretty simple, and they make us feel good. But as much as we would like it to be the case, life is not made up of only the natural log and the natural exponential. So this other is what that refers to. So what about y equals a to the x? What about y equals a to the x? Other exponential functions, other bases other than e. Well, that's what we're going to focus our attention on, and probably also come back and look at logarithms of different bases. Okay, but for today, we're just going to look at the exponential of a different base. Well, before we do that, we're going to again recall something that we saw on Friday, which is that we had a pretty funny way to define a to the x if we wanted to. We could define a to the x in terms of the natural exponential function by realizing that we could say that y equals a to the x is the same as e of the ln of a to the x, because the e to the ln cancels out and you get a to the x. And more specifically, we can use the power rule on the ln to say that a to the x is equal to e to the x times ln of a. And I'm just dropping this down. And so as we develop our understanding of what the derivative of a to the x is for some general a, this is what we're going to use to figure that out. Because this is something we can differentiate based on our prior knowledge of the natural exponential function. So we're going to differentiate this guy. So we'll let this be f of x. Then f prime, the derivative, is going to be the derivative of e to the x times the ln of a. which should be e to the x times the ln of a times the derivative of x times the ln of a. All I'm doing is applying our pre-existing rule for differentiating the natural exponential function. It's itself times the derivative of whatever its exponent is. Let's consider what the derivative of x times the ln of a needs to be. What's the ln of a? No. More generally, ln of a is just some base. Could be 2, could be 7, could be 18 million. So the ln of some constant is a constant. It's just a number. So I know this looks like some changing variable thing, but ln of a is a number. And if we're differentiating a number times x with respect to x, what is the derivative of that? What's the derivative of 5x? What's the derivative of 17x? So what's the derivative of ln of a times x? Ln of a. So this turns into e to the x times the ln of a times the ln of a. But then in some real trickeration, let's not forget what e to the x times ln of a is. A to the x. And so the derivative of a to the x is a to the x times the ln of a. A little bit peculiar, but we're okay with it. Or then more generally, dx of a to the u is equal to a to the u times ln of a times dx of u. Again, having to sort of account for this chain rule situation. Whoa. So let's see an example out in the wild. What are we going to do? Example 1. It's a good enough place to start. Probably box this up. Probably box that up. Yeah. Example 1. Some function f is defined by 3 raised to the x squared power. Whoa, whoa, whoa. Great, great. Find the derivative of f. Okay, and actually before we do this, I want to sort of, again, try to make abundantly clear that this is a new and novel arena for us, okay? Because a to the x is not the same as x to the n. And this came up, I think Sean asked the question, why don't we just drop it down and subtract 1? Because these are two different functions. Here, the dependent variable is our exponent. Here, our exponent is fixed, and what's changing is our base. Exponential, power. Exponential, cube root, 4th root, 7th root. These are different functions. And I know that because we have variables in both places, because these are the general forms of these equations, they can look pretty similar, but these are not the same. Hopefully looking at this function, you're kind of like, oh yeah, that's not something we've seen before in terms of trying to differentiate. Okay. We've seen x raised to the third power, but not 3 raised to the x power. They're two different situations. And so now we're going to use this rule to attack this new situation. And so f prime, according to the rule we just figured out, is going to be a to the u, so 3 raised to the x squared, times the ln of a, where a is our exponential base, so ln of 3, times the derivative of that exponent, x squared. The derivative of x squared is 2x, and so we'll write this as 2x times 3 to the x squared times ln of 3. And here you're going to have to strongly resist the algebra 1 urge to multiply the 2 and the 3. Don't do that. Do not do that. Order of operations. You can't just barge your way into an exponential situation. As uncomfortable as it is to write an answer like this is the answer. There's no further road to walk here. All right, cool. Cool. Maybe not super cool, but we're at least kind of like, okay. But now the question is, what about the other direction? Because so far we've had all these two-way streets. Differentiate, integrate. Differentiate, integrate. What do we integrate to get back to a to the u? Well, I'm gonna give you what the rule is, and then we'll just do a quick check. So the other way, integration, says that the integral of a to the u is equal to a to the u times ln of a plus c. Let's check. How do we check? We'll differentiate this guy. Make sure that we get a to the u. Well, the derivative of a to the u over ln of a, again, understanding that ln of a is just a constant, is equal to 1 over the ln of a times the derivative of a to the u, which is a to the u times the ln of a. Oh, that's convenient. Derivative of some constant c with respect to x is just 0. The ln of a and the 1 over ln of a conveniently cancel out, and we do indeed get a to the u. So this is our other way down that street. So we've got rules for the natural situations, the ln and the e situations. Now we have rules for the arbitrary, any flavor exponential function, both differentiating and integrating. So basically this last chapter that we're covering is sort of filling all the little gaps in our differentiation and integrating knowledge. Let's see an example of this. And the book kind of cranks it up pretty hard right away, but you know, that's okay. Nice to have like a little softball example, but I guess you're calc students, you can figure it out. Example 2. Example 2. They want us to find the integral of the square root of 10 raised to the 3x. That's a funky looking thing. Dx. We're sort of like Smithy, like I see there's an exponential in there, but it's kind of trapped inside of a square root. What are we going to do about that? Well, what we're going to do about that is change its appearance and see if that helps. Meaning instead of this square root radical situation, we're going to call this 10 to the 3x raised to the 1/2 dx. And then even further than that, we're going to say, oh, we know we can even write this exponent a little more compactly because we can multiply these exponents. And so we'll get the integral of 10 raised to the 3x over 2 dx. And now we're like, okay, that sort of looks like an a to the u situation. That looks like an a to the u that we just 30 seconds ago learned about. But it's like kind of funky because the exponent is sort of a function and we want it just to be like a u or a single variable. So what do we do when we have things that are more complicated than we want them to be? We do a u sub, okay? And so we're going to do a u sub on the exponent because what we want is an exponential function, which we have, but there's like a composite linear function hidden inside that exponential function. And so we're going to take care of that by saying that u, this will be off to the side here, let u equal 3/2 x, which means that du is equal to 3/2 times dx, which means that dx is equal to 2/3 times du. And now we can do some substitution. Instead of 10 to the 3x over 2, we'll have 10 to the u. Instead of dx, we'll have 2/3 du. And now we can integrate this guy. The 2/3 can just come out front. The 10 to the u is going to turn into 10 to the u, turn into 10 to the u divided by the ln of 10, divided by the ln of a, which in this case is 10, plus c, and then subbing back in for u, we end up with 2 times 10 to the 3x over 2 divided by 3 times the ln of 10 plus c. And again, like this is going to be a constant temptation for you. This is not 20 raised to the 3x divided by 2. You do not get to multiply those things. If you're still sort of like unsure about that, consider if this was 2 times 10 squared. What's 10 squared? It's 100. So 2 times 10 squared is 200. What you're really, for some reason, wanting to do, not for some reason, it's human nature. You want to make it look simpler. You're trying to say that 20 squared is the same as 2 times 10 squared. What's 20 squared? 400. Those things are not the same. which is why we do not multiply those things. I know that can kind of get lost sometimes. Yes, you could do that. So Mario asked if we wanted, could we write the denominator as the ln of 10,000, of 1,000 rather, by using the power rule? Yeah, you could do that. If you wanted to, you go 2 times 10 raised to the 3x over 2. This 3 could then be an exponent inside here and turn this into ln of 1,000. That could be a nice way to clean that up. Okay, so that's that. What else do we need to get through? 720, oh boy, oh boy. Where else are we going? Where else are we going? So many places. Oh boy, that was longer than I thought it would be. Yeah, all right, example 3. Example 3. Now we're gonna put this to use with some area. That's gonna be fun. Example 3. I think it's read. That's not what we want. 5.4. 5.5 rather. Okay, so example 3 says sketch the graphs of y equals 2 to the x and y equals 2 to the negative x. And then find the exact area of the region bounded by these two graphs and the line x equals 2. That sounds hard. Let's do it. Y equals 2 to the x and y equals 2 to the negative x. Straight edge, please. Scalpel. What are you talking about? I don't know. Go boom. Let's go one more. There. Not going to need any negative y's here because these are both exponential functions. We'll go like 1, 2, 3, 4. And then like 1, 2. Okay. So hopefully from our Algebra 1 days, we're okay with y equals 2 to the x. Okay, it's got a y-intercept at 1 because 2 to the 0 is 1. It hits 1, 2 because 2 to the first is 2. It hits 4 because 2 squared is 4. It hits negative 1, 1/2, negative 2, 1/4. It ends up looking something like, nope, not my best exponential curve, but you get the picture. We're like, okay, cool. What about 2 to the negative x? Well, this negative represents a reflection over the y-axis. We're actually doing this exact thing in geometry right now. We're looking more at figures, but when you make all of your x's negative, it flips it over the y-axis. Okay? And so this curve is this curve reflected over the y-axis, which also makes sense analytically, because if you plug in a -1, for example, 2 to the -1 is 2 to the first, so we get this point. Or -2 becomes a +2, and we get a +4. They share a y-intercept, and then they're just reflections of each other. So this curve looks like that. Here's y equals 2 to the negative x, y equals 2 to the x. That was part A. What they want from us is to determine what is the area bounded by those two curves and x equals 2. What is this area in here? Well, since we're a little crunched for time, I'm not going to set up the Riemann sum, but there are some rectangles in here that we could draw. Whose heights are the difference between 2 to the x and 2 to the negative x. We could then turn into an integral. The area would be the definite integral between 0 and 2 of 2 to the x, the top of our rectangle, that curve, minus 2 to the negative x. And we now are equipped with the proper knowledge to integrate 2 to the x. Where 30 minutes ago, we were not. So this is going to turn into the definite integral from 0 to 2 of 2 to the x dx minus the definite integral from 0 to 2 of 2 to the negative x dx. The left-hand part of this goes pretty smooth, okay, because there's no chain rule that needs to happen. This just turns into 2 to the x over the ln of 2 from 0 to 2. Okay, are we okay with that? This is like a very basic, straightforward exponential antiderivative. 2 to the x divided by ln of 2. Over here, we got to kind of deal with that negative. So we're going to do a quick u sub, letting u equal negative x, meaning that du is equal to negative dx, or that dx is equal to negative du. And so this will become minus the integral from 0 to 2 of 2 to the u times negative du. We'll see what's happening here. This is going to turn into a sum. Okay, so kind of doing two things simultaneously. We'll start evaluating this guy and then integrate this guy. So evaluating this guy gives us 2 squared, otherwise known as 4, over the ln of 2, minus 2 to the 0, otherwise known as 1, over the ln of 2. Over here, this turns into a plus the negative du. You pull out the negative, and this turns into a plus. And this integrates just the same way. We end up with a 2 to the u over the ln of 2 from 0 to 2. 4 over ln of 2 minus 1 over ln of 2 should just turn out to be 3 over the ln of 2. Here we've got plus. We got to sub back in for u. We got to be careful not to miss that point. 2 to the negative x over the ln of 2 from 0 to 2. And so we get 3 over the ln of 2, plugging in 2 and 0. 2 to the negative 2, excuse me, is 1/4. So we get 1 over 4 times the ln of 2. 0, when it's negative, is still 0. So that becomes a 1 over the ln of 2. And so I feel like I made a mistake here. Let's double check. So 1/4. No, we're good. So then this turns into 2. 3 minus the 1 gives you 2 over the ln of 2 plus a quarter, 1/4 over times 1 over ln of 2. And so then if we want to combine these, we can write 2 over ln of 2 as 8 over 4 times the ln of 2. Noticing that the 4 and the 8, I need to extend this. Is that better? There we go. 8 divided by 4 is 2, plus 1 over 4 times ln of 2. Common denominators, we finally get to 9 divided by 4 times ln of 2. And yes, Mario, if you wanted, you could write ln of 4 times the ln of 2 as the ln of 16. That was fun. Whew. Do we have time? Do we have time? Do we have time? We'll make time. Yeah. Questions about that one? Breakneck pace.
How did you get from that step above to the 4 over ln of 2 minus ln of 2?
This guy?
Right at the top, one more or two more lines. Yeah. How did you get to that from the step above?
Plugging in a 2 to the x gives you 2 squared, which gives you 4. Subtracting what you get when you plug in 0. 2 to the 0 is 1.
Okay, gotcha. Yeah. Thank you.
That? Good? Okay.
Yeah, thank you.
Sure. Okay, so then we got one more example. That's actually 2 examples, but it's the same problem, just done 2 ways. I think we'll pull it off. Okay, so this is just showing that we now have the ability to do areas, and I think your homework actually does a volume question as well with exponential functions, which, you know, it's kind of cool, kind of fun. And it works just the same way as we would expect. We just need to know how to integrate exponential functions. Okay. The final one gets a little weird, but we're all a little weird, so that's okay. This will be example 6 and 7. 6 and 7 combined. So examples. 2 for the price of 1. 6 and 7. And we have the function y equals x raised to the x power. What? That ain't right. Yeah, I know, it's kind of strange. And they want us to find the derivative of y. Don't do us like that. Yeah, they're doing us like that. And so there are 2 pathways to success that we can follow here. Maybe there's 3, I don't know, but I only know 2 of them. Called first one method 1, because why not? Method 1 is just charge, just do it directly. We're going to say, okay, y equals x raised to the x power. Realizing that in our kind of conception of life, we know how to handle a to the x, okay? And we know that a to the x is equal to e to the x times ln of a. That was sort of our trick for arriving at the derivative formula. Okay. And so here, in x to the x, it's kind of bizarro, but our a is x. So So we've kind of like merged like the exponential function and the power function. Kind of strange. But that means that if we want to use this sort of language, x to the x then is going to be equal to e to the x times ln of x. In our kind of more wholesome normal example, it was ln of a, but here our a is x. Here our a is x. And I tell you all that just so that we don't freak out when I write the next step, which I'm going to say is that y is equal to e raised to the x times ln of x. It just follows from our previous definition of a to the x, and understanding that in this case, our a is also x. Well, now this is something that we can more easily differentiate. Okay? And so we'll say that dy dx is equal to the derivative of this guy. Well, the derivative of that guy is itself e to the x times ln of x times the derivative of its variable, of its exponent, rather. The derivative of x times the ln of x. Well, that's chain rule, sorry, product rule. So e to the x times the ln of x. The derivative of x times the ln of x is going to require the product rule. So we'll do the derivative of the first thing. The derivative of x is just 1 times the second thing, ln of x, plus the second thing, sorry, the first thing times the derivative of the second thing. What's the derivative of the ln of x? 1 over x. Oh, whoa, that's kind of fun. And so the derivative of x times the ln of x turns out to be the ln of x plus 1, because the x and the 1 over x cancel out. But then in a real nice twist, e raised to the x times the ln of x was our starting function. Remember, we did this sub at the very beginning and said that x to the x is the same as e to the x ln of x. And so our final form of the derivative, we're going to say, is equal to x raised to the x times the ln of x plus 1. Cool. Cool, cool. I said there was 2 methods because this is example 6 and 7. So let's see method 2.
Mr. Smith,
What's shaking?
how do you get the x times 1 over x? Where does that come from?
The product rule of the derivative here, x and ln of x are both functions of x. So when we differentiate, we have to use the product rule. And the product rule says take the derivative of the first thing, which is x. The derivative of x is 1 times the second thing. 1 times ln of x gives us ln of x. And the second half of the product rule says take the first thing times the derivative of the second thing. The derivative of the second thing, ln of x, is 1 over x. So the x times the derivative of the second thing. This is first thing, derivative of the second thing. This is derivative of the first thing times the second thing. And that's product rule. There's a 1 here that I didn't write because I just didn't. Good question. Okay, method 2 is going to be to attack this implicitly. Okay. So writing this as y equals x to the x, but then hitting both things with a ln. Hitting both things with a ln. So the ln of y is now equal to the ln of x to the x. Oh, that's kind of sassy. Because now ln of x to the x, we can drop that bad boy down. And now we're looking at the ln of y equal to x times the ln of x. So we'll kind of circle back to your question tray and have this derivative again to look at. But now we can differentiate this whole thing with respect to x. On the left side, the derivative of ln of y is 1 over y times, remember, if we're differentiating with respect to one variable and we come across another variable, we should assume that that is a function. We're not assuming, we know that y is a function of x because we started there. And so this pops out dy dx, which is what we're after. On the right side, we get another chance at differentiating x times the ln of x. And we're going to take the derivative of the first thing, which is 1, times the second thing, plus the first thing times the derivative of the second thing, which is 1 over x. And so we end up with 1 over y times dy dx is equal to the ln of x, and we again get the x times 1 over x to go away. But we want the derivative by itself, so we get dy dx is equal to y times the ln of x plus 1. And oh, happy day, what's y? X to the x. So we arrive at the same destination. Oof. Uh-oh, Edgar's trying to get back in. Didn't realize he had left. Somebody was supposed to remind me to amend the homework. Let me take a quick look. I kind of just want us to do the greatest hits, because I know that we are sort of drowning you in mathematics right now. Okay, so new share, let's do screen 2. Here we go, 5.5. Let's see what they got. 1, that's fair. 5, that's fair. 9, sure. Oh, maybe not 9. Okay, so for now, so homework 5.5. Skip. So the assignment sheet is good, but we're going to skip, and I'll project this in a second. Maybe I should just do this now. Let's do a new share. Let's do a new share. Advanced camera share. Skip. Now I can't see that, so that's an issue. Here we go. Edgar, I said you could come in. Come in, bro. Skip number 9. Skip number 11. Oh, 15, now you're doing that one for sure. 21, we're good. 31, do we need to do that? No, we're gonna skip 31. 31, I don't care about. 37, we're skipping. Bro, I am just hooking you guys up. 53, what's 53? 53 is good. Yeah. Yeah, so basically cutting the assignment almost in half. Okay, so the question that should be lingering, and we will probably address this tomorrow, is what happens if we have a logarithmic function with a base other than e? Because that's sort of the final side of the coin. We looked at the natural log, we looked at the natural exponential, we looked at the generic exponential today with any base. What about the generic logarithmic of any base? How do we differentiate that? So we're not quite done with this part yet. Okay, and again, tonight or during first, I will post the videos for 2018 FRQs. So they should be on my YouTube if you really want to hunt them down. I will make sure to link those directly from that document. Whew, we did it. Uh-oh. Chat. Could I move my paper up? Yes, I could. You guys are free to go, and we'll see you tomorrow.
Bye, thank you.
You're welcome. How far up do you need to go, Edgar?
Method 1.
Method 1. There we go. You're welcome.
Mr. Smith,
What's shaking?
are there problems we're skipping? Are we skipping only for tonight or like for the entire assignment?
Just for tonight. We'll probably come back to them. But you will not be able to do those problems with the knowledge that we have gained today.
Okay, thank you.
Yep. You're welcome.
Do.
You may. What's up?
So just on the quiz, you said my notation was wrong. Was it because I put the X?
Yes.
And there should no be.
So when you're doing a sigma notation,
Yeah.
in order for actually to sum something, you need the index of notation involved. So you had it there.
Oh,
but
so the X squared should have been
like
X
W sub I.
W
Yeah,
sub
or
I.
yeah, whatever variable you want.
Okay.
Because that's sort of a nonsensical summation.
Okay, that makes sense. Thank you.
I only docked you like what, 2 points?
Yeah, just do.
Okay.
Thank you.
But now you'll remember. You're already into Brown. Like, come on, second semester senior. Are they going to let you guys on campus next fall?
Yeah, because I think everyone is there right now.
Okay.
So hopefully.
Fingers crossed.